Hi everybody, section 10.8, geometric probability. Okay, you probably remember a bunch of problems from middle school and so on where you looked at probability. That was the chance of what you wanted to happen divided by all the possibilities. Okay, so you probably did a bunch of problems involving flipping coins or rolling dice or pulling socks out of a drawer, things like that, and figuring out what was the probability of getting two red socks or matching up blue jeans and t-shirts and things like that. We're going to take it a step further in terms of geometry and geometric probability, where we're going to be looking at areas in order to find out the probability of something happening at lengths or areas, okay, in order to find the probability that an event might occur. Okay, so we're going to take probability and link it up with geometry, and that's what we call geometric probability. So I'm going to start with kind of, I hope, a fun example. I don't know who these people are, but they sure look like they're having fun playing miniature golf. All right, so we're going to make a couple assumptions about this hole. Okay, we're going to say that this area here, the first thing we want to do is hit the ball in that center hole. Okay, and I'm going to assume later on that this whole length here from side to side is, let's say, 48 inches, and my little target here is 6 inches. So we're going to have to figure out the probability that if we were making a random shot, okay, not aiming, and we'll talk about that a little bit later, what's the probability that we're going to get in the little hole out of a total length, a 6-inch hole out of a total length of 48 inches. Then we're going to assume that that hole leads us through a pipe and deposits us on a green. And then we'll figure out we'll use another way of looking at geometric probability to figure out the chances of getting a hole in one. So let's go on into it, see what we got. So the first thing we got to do, assuming that we got a 48-inch target here, okay, from side to side, and my good area that I want to hit is a 6-inch hole in the middle, 6-inch gap in the middle. We're going to have to hit that first, and then again assume that once we hit that, we're going to pop onto a green that's 4 foot by 6 foot and has a little hole right here with a 2-inch diameter, 4-inch diameter, 2-inch radius. Okay, 4-inch diameter, 2-inch radius, get the ball in the hole. Now, the key towards using geometric probability is that everything has got to be totally random. So even when I'm aiming at this first hole, we're going to assume that I'm not really aiming, okay? I'm going to hit somewhere on this 48-inch width, but not really aiming for that 6-inch, so it's a random possibility that I could hit here, 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 any of those possibly random, okay? And, as I say here, if you've seen me golf, you would know that the way I putt, it is totally random. Okay, so first of all, we got to hit this 6-inch gap in a 48-inch length. Then assume that that ball is going to drop randomly onto this area and figure out what's the probability that we have a random ball, the chance of landing in the hole out of this entire area. All right, so remember, probability is the ratio, what you want to happen divided by all the things that could happen. And then at the very end, we're going to multiply it by 100 to get a percentage. So let's look first at this part. We need to putt into the 6-inch gap out of a 48-inch total space. So what we want to happen is hit that 6 inches. All the things that could happen are 48 inches worth. All right? So we take 6 over 48. That simplifies to 1/8 or 0.125. Okay. For the second part, dropping a ball on this green so that it lands in this little hole. Well, the area of the little hole, what I want is pi r squared, the total possibility of a 4 by 6 foot screen area. Okay, converting it all to inches, that's 48 inches and 72 inches. So I've got a probability of 4 pi of what I want to happen out of 48 times 72, or 3,456 square inches that it could land in. That leaves me with a probability of 0.0036. Okay? Two events in tandem like this, with one depending on the other. This is called compound events. We'll talk about this more later in the book. To find the probability of the pair happening, we multiply the two together. So, take our 125 from the first event, our 0.0036 from the second event, and we get this little tiny number here. Now we can multiply it by 100 to find the percent probability, and it tells us that if we shot it 100 times, I'd make a hole in one 0.045 times. To put that in a little bit of another perspective, what we're saying is I could take 10,000 shots and I'd make a hole in one 4 or 5 times. Okay? But that's really just kind of an illustration of two of the ways we use geometric probability. One, in terms of straight lines and a length in terms of a total length. And two, in terms of an area that we want divided by a total area of all the things that could happen. Okay, so let's look at a little more practical examples here. Okay, so geometric probability uses points on segments or in a region on a plane to represent outcomes. Okay, the geometric probability of event is a ratio that involves geometric measures such as length or area. So that first part of the problem, this one, okay, involved a length. And we can use that kind of thing for anything that's linear, anything that moves in a straight line. All right? So it could be 6 inches out of 48 inches if we're putting a ball randomly, or we can consider a straight line model for any number of things. For example, I'm going to look at a time example. I know that there's a city bus that stops on a certain corner every 25 minutes. Now, if we randomly arrive at that corner, what's the chance that we have less than 5 minutes to wait for the bus? Okay, so let's take a look at it. We can consider it to be a straight line kind of model. I know I have a time 0 when the bus leaves, and the next bus comes at 25 minutes. I also know if I want to have a 5-minute wait or less, I've got to arrive somewhere after this 20-minute spot, right? So this red area is our red zone. That's when we want to arrive. If we arrive there in any of these times, we have less than a 5-minute wait. So the probability of looking at what we want to happen compared to all the things that could happen, we've got a 5-minute window of what I want to happen, 25 minutes total. That's a 1 out of 5 fraction. We multiply it by 100%, and we know we have a 20% probability of arriving at the bus stop within 5 minutes of the bus coming to pick us up. Make sense? So straight line models work for time and for distances. Now the second part of our problem with the golf course, okay, involved areas. I need to know the good area, right, landing in the hole, compared to all the total area that could happen there. So let's look at another example that might use that. Okay, you're at an amusement park. You're playing a carnival game. You're going to throw a dart at a board. It's got 12 balloons on it. Now, each balloon has a 3-inch radius, and the entire board is 5 feet by 6 feet. Now, you're blindfolded, so every throw is random. All you know is you're going to hit the blue area somewhere. What's the chance that you pop a balloon? Okay, think about it. Here's the answer. Once again, all the things you want to happen divide all the things that could happen. Well, what I want is to hit a balloon. So I got 12 chances to hit a balloon, and the area that goes with it, pi r squared for each balloon. If it's got a 3-inch radius, pi r squared gives me the area. I got 12 of those areas. That is the total area of the red dots on that figure. Now, the total area of the blue space is 5 feet by 6 feet, or once again changing it to inches, 60 inches, 72 inches. So the probability of what I want to happen is 12 times pi times 9, or 339. And 60 times 72, 4320. We multiply that by 100%. I've got a 7.85% chance of hitting a red balloon out of all that blue area. Make sense? Good. Let's look at one more example like that. Now, we're also at a carnival game. We're throwing a dart again, but the target looks like this. And mostly I'm doing this to remind you how to do areas of polygons. But we're going to look at this. We want to hit a red area in order to win a prize. So if everything's random again, what's the probability we're going to hit a red area? Okay, once again, what we want to happen divided by all the things that could happen. In this case, the red area divided by the total area of the hexagon. Now, this gets a little trickier here because the red area is the total area of the hexagon minus the big old hole in the middle, minus that area of the circle, all divided by the area of the hexagon. So, the area of the circle is easy. The radius is 10.4 inches, so pi r squared gives us 340 inches for the area of the circle. And on the next slide, we're going to plug that in right here for the area of the circle. All right? But now we got the tricky part. Let's find the area of the hexagon. So going on to the next page, we look at the area of the hexagon, and we remember our tricks from earlier in the chapter. Okay, the central angle for all of these congruent hexagons that we've got to make up, congruent triangles to make up this hexagon here, we remember that central angle would be 360 divided by 6. Or, in other words, if I look at this figure right here, that thing right there is 60 degrees. Let's undo those though, because we really don't care about the 60 degrees other than it gives us a 30-degree triangle with a right angle right here when we drop that altitude. Okay, so we've got an apothem of 10.4, we've got a 30-degree angle, and we can use our 30, 60, 90 rules if we want. I've chosen to do it by trig. So remember that the tangent of 30 is the opposite over the adjacent, or the tangent of 30 is x over 10.4. Multiplying across, x is going to be 10.4 times the tangent of 30, and that comes out to be 6. So I know x is 6, which means this entire side length must be 6 plus 6, or 12, right? And if that side length is 12, the total perimeter is 6 of those sides, or 72 inches. So the area of the hexagon then, 1/2 apothem times perimeter, 1/2 of 10.4 times the perimeter of 72, is 374 square inches. Now going back to our probability formula, what we want to happen, divided by all the things that could happen, well, the red area is the area of the hexagon minus the circle. All the things that could happen is hit the area of the hexagon. So, hexagon minus circle divided by hexagon times 100, we've got a 9% chance of hitting a red zone there. Make sense? All right, we'll get to play with this a little bit later on. Chances are good that I will see you soon.